students, and welcome back to Study Room. So, as I told you, today we're going to start about magnetic effect or magnetic field due to a current carrying conductor, which is what this chapter is all about. So, in the last class, we studied about magnetic field, what magnetic field is, magnetic field lines, where we say magnetic field is stronger based on the closeness of the field lines and the properties of the field line. So, now we're going to start with the next topic, which is the magnetic field caused due to the current in the conductor. Now, direction of flow of current due to magnetic effect of electric current. Now, this was also something that was experimentally seen or experimentally observed. So, you saw in the first, when we talked about the experiment that Hans Christian Oersted accidentally discovered the magnetic property of electric current, that when a compass needle is kept near a current carrying wire, it gets deflected. So, a further experiment was conducted in it by seeing that if we change the direction of current. So, how do we change the direction of current? If this is a circuit, say this is the resistor in the circuit, and you have a key here and you have this battery, right? So we know this is the positive terminal, this is the negative terminal. We know current flows in from positive to negative. Now, if in the same circuit, I want the current, so if we want to reverse the direction without changing the circuit, what do we change? We just change the way we put the battery, right? How? Look at this. This is the key. The resistor is at the same place. If I just make the battery with its negative here and positive here, what will happen? The current flows in the exact opposite direction to what it was in the previous case, right? So that is what they did to see that does the deflection of the needle, the direction in which the needle gets deflected, depend upon the current direction. Let's see what happens. So it said that the direction of magnetic field produced by the electric current. So we've established that the electric current produces a magnetic field. Why? Because the compass needle gets deflected by it. So this we have understood by now, that the magnetic field is there because of the electric current. Great. So now we say that the direction of magnetic field produced by the electric current is reversed. That is, it is actually changed when the direction of flow of electric current is changed. That means the direction of the magnetic field. And why direction? We learned that magnetic field is having both direction and magnitude, right? So that is why we're saying the direction of magnetic field, because we saw that it goes either from the north to the south or inside from south to north. So we are specifying some kind of direction to it, right? We're not just saying magnetic field is like anywhere in the air. No, we're specifying that outside the magnet from north to south, inside the magnet from south to north. So it has a specific direction to it, right? So we see that when we change the direction of flow of current in the current carrying conductor, the compass needle gets deflected in opposite directions in both cases. That means that direction part of the magnetic field is changed. That means it depends on the direction of current. Okay. Look, so it's shown in the figure. The first figure, which direction is the current flowing? The current is flowing like this. And in the second figure, the current is flowing like this. So we see that in the first way, the first case, the compass needle gets deflected towards east. It's written here. But in the second case, it gets deflected exactly to the opposite, which is west. So now we know that the direction of the magnetic field depends on the direction of flow of current. Okay, we don't know that if it's flowing clockwise, would it get deflected to east-west? That is completely experimental. You just need to know that it changes. If it's deflected to the east in one case, when we reverse current, it is going to get deflected to the west. Okay, great. Now, magnetic field due to a straight conducting wire. So, what does a straight conducting wire mean? Look at this. Look at this figure. There is a resistance, an ammeter, one battery, a key, and this. What is this thing? It is nothing but we've taken this piece of paper, and just think if you take this piece of paper and you just put a wire through it. Like you take this like this and you take the wire through it. Like if this is the paper, if my hand is the paper, and I put a wire through it. This goes from here and it comes out of here. I make a hole in the paper and the wire goes straight through the hole. So if we want to study the field due to a wire, so what are we basically doing? We are studying the pattern or the way the magnetic field forms in case of each and every kind of magnet. We saw in case of bar magnet, we saw it is those closed curved loops going from north to south. But here there is no north or south per se. There is only a field, right? We know there is only a magnetic field. So now we want to see it due to a straight conducting wire. So we do this. We put it through this piece of paper. And how do we see what is the direction of the current through it? Sorry, so what does the magnetic field lines depends upon how we see it is, we on this paper, what do? What did we do in case of a bar magnet? We threw some iron filings on it, small pieces of iron, so we put it on this paper. Okay, right now there is no current through it. Right now the key is open. So what does current flow through it if the key is open? No, right? It does not. Sorry, this is the negative side, right? In the figure, I'm drawing it according to the figure only, right? So here I'm not connecting the ammeter. That's all additional only. I have a resistor here also. So right now the key is open. The circuit is not complete, so current is not flowing. So what do? I put these iron fillings randomly. Okay, I just sprinkle the iron fillings on the piece of paper, right? So we learned that there is a magnetic field due to the current in the wire. So right now, is there current in the wire? No. Why? Because the circuit is open. So can current flow? No, because the circuit is not closed and continuous. We've already studied this. So there is going to be no magnetic field also in this wire. Say AB, we've named it. No magnetic field. But as soon as we close the wire, as soon as we close the switch, what happens? The circuit is complete. So current flows like this, right? So now if we, this piece of paper, if we gently tap it, not like hit it, but if we gently tap it with our fingers, we will see that these iron filings, what will happen? These iron filings that were randomly we had thrown onto the paper, they would get arranged like this. Okay. They would get arranged somewhat like this. They'll not go outside the paper, my bad. But they will get arranged like this. Now you can see it in the figure also. So what does that mean? That magnetic field lines. Now don't get confused with the bar magnet. Like in the bar magnet, they were like these loops, curved loops from north to south. That is different. That is for a bar magnet. For each magnet or for each shape, the type of field lines are going to be different. The properties don't change. The field lines are still continuous. They are still curves. No two field lines interact or touch each other. Wherever the field lines are very close to each other, the magnetic field is very strong. All those properties definitely remain same, but the shape or the way the field lines are formed is different for each and every single conductor. Okay. Now, in case of this field line or in case of the single current carrying conductor, straight. So this is important. It is straight conducting wire. Okay. It is not in the form of a circle or a loop. It's completely straight. So we see that magnetic field lines are in form of, what do we call these? If this is where the wire is going from and the field lines are being formed like this, what do we call this pattern? What do we call these circles which have the same center? They are known as concentric circle, in the form of concentric circles with wire in the middle. Okay, that is how the field lines are actually formed in case of a straight conducting wire. The field lines are in the form of concentric circles with the wire in the middle. You can see it here. Now what I've purposefully shown you here, look at this. These two field lines, how close they are, and these two field lines. So what does that mean? That means that near the wire, the field lines are closer to each other. So, is magnetic field stronger or weaker? Stronger. And as we go a little far, the field lines are becoming more farther. So, what was the property of field lines? If the field lines are crowded, magnetic field stronger. Not crowded, far away, it is weaker. So, as we go away from this current carrying wire, the magnetic field gets weaker. We'll study about this. There are some properties given which are going to do now. Now, look at this. Magnetic field due to a straight current conducting wire, we're going to study about it. So, we see that the deflection in the needle. Okay, so one thing that I forgot to tell you was that paper that we had through which we put that wire, if we keep a needle also, what is this needle? It is nothing but a compass needle. Okay, we keep a compass needle here, north and south. Right. So we see that there is a deflection in the compass needle also. So that only confirms that there is a magnetic field being generated by that current carrying wire. Yes. Okay. Now we see that the deflection in needle increases if the current is increased. What does that mean? The current is increased means that we know that V is proportional to I, Ohm's law, right? So if the current is increased, to increase current, we would have to increase voltage. That means if a 6-volt battery was used, we replace that and we use a 12-volt or a 6, 7 or a 7, 8, 9, just more than 6-volt batteries used. That means current increases. So when current increases, the deflection in the needle increases. What does that mean? If the deflection is increasing, that means the field is going even stronger, right? So there are two people. One is a 3-year-old boy and one is a 10-year-old boy. So the 10-year-old boy pushes the 3-year-old boy. He pushes with some force, right? But if he is replaced by a 20-year-old man, when he pushes the 3-year-old boy, very dangerous example, don't do this. But if he pushes a 3-year-old boy, would the 3-year-old boy feel more force? Would he be pushed away with more force or lesser force? The 20-year-old will obviously be stronger than the 10-year-old, right? So he'll be pushed away with more force. So similarly, here also, when we increase the current, the deflection in the needle is more. That means the needle is being pushed away or the force on the needle is even more. What does that mean? That the magnetic force has increased. That means the magnetic field has gotten stronger. Okay. So this indicates, let's read in the PPT, this indicates that the magnitude of the magnetic field, again we come back to magnitude and direction. These are the two things in the magnetic field. So direction and magnitude. So direction cannot specify the force by it, right? So if the magnitude is 4 and the direction is towards the left and we change it to right, would the force increase? Just think about it. If the 10-year-old boy is here, the 3-year-old is here. If he pushes the 3-year-old towards this side, then the 3-year-old comes here and he pushes him towards this side. Would his force change? No, right? It's the same boy. That means he has the same magnitude. But it is only a greater magnitude when he is replaced by a bigger boy. That means when the magnetic field is replaced by a stronger magnetic field. So what has to change? The magnitude of the magnetic field has to change. Okay. So let's read again. This indicates that the magnitude of the magnetic field produced at a given point increases as the current through the wire increases. This was also experimentally observed. We saw that, okay, let's change the current. Let's increase the current. So we see that the needle gets deflected even more sharply, which means that with the increase in current, the magnetic field also increases. Okay, let's see the second thing that happens here. That the deflection in the needle decreases when the compass is placed far from the conducting wire. I showed you that with the help of the field lines, right? So if this is the wire, near the wire the field lines would be like this. But as we keep going farther and farther, the field lines, the gap between the field line keeps on increasing. What does it mean? That with increasing distance, force or intensity decreases. Force or intensity of what? The magnetic field. So let's read in your PPT. It says that the deflection in the needle decreases when the compass is placed at a far distance from the conducting wire. So the magnetic field produced by a given current in the conductor decreases as the distance increases. So you can't do both the things. You can't increase the current and increase the distance also. We've done this before also. If you want to observe the changes because of one variable, you keep everything else constant. So if you want to see how much of a difference there is in the magnetic field when we change current, so then you don't change direction. You only keep the needle at one distance and you increase the current and you see the deflection. Second thing, if you want to see with the distance, you keep current constant. So you use a 6-volt battery. Only if you're using a 6-volt battery, you keep the compass near to the wire and keep taking it far away to see the deflection, how it changes. Okay, great. Now, this is a very interesting rule which is going to help you to determine the direction of the magnetic field that we've been talking about for so long. What is the right hand thumb rule? Let's read first and then I'll explain it to you. So what this rule basically does is, it lets you know the direction of the magnetic field that we have been talking about for so long. So let's read how we actually do it, then I'll explain it to you. So it says that if we hold a current carrying conductor in our right hand such that the thumb points the direction of current, then the fingers curled of the hand indicate the direction of magnetic field. So what does that mean? Let's go line by line. So it says, if we hold a current carrying conductor in our right hand, okay, hold your right hand up, this is your right hand, and you're holding a current carrying conductor in your right hand, such that, think if you are given a wire, you have to hold a wire. How would you normally hold a wire? You would hold it like this. But just for this rule, you don't hold it like this. You hold it in a way that your thumb is not touching the wire, or thumb is outside. Okay, so you are given this wire. Say this is the wire. You are given this wire. So instead of holding it like this, you hold the wire like this. Okay, now, so it says if we hold a current carrying conductor in our right hand such that the thumb points in the direction of current. So the next thing you need to do is, you need to look at the direction of your thumb and you need to point it in the direction of current. So if this is the wire and the current is going upwards, so how will my thumb be? My thumb will be like this, upwards. But if the direction of current is downwards, how will my hand be? How will my thumb be? I will hold it like this, so that my thumb is pointing in the direction of current. That is what we have to do in the rule only. Okay, so what does that tell us? That tells us that the direction in which our fingers are curling is the direction of the magnetic field. So right now we've learned that if this is the wire, there is current through the wire, and we know that the magnetic field around the wire, if I am not drawing the paper now, I know the magnetic field is like this, right? I'm not drawing the paper and the iron filings, we've already learned that. But we know that magnetic field lines can't just be like a normal circle. It has to have some arrow in it because it has a specific direction, right? So what is the direction going to be? How do we know if we draw the arrow like this or like this? How do we get to know that? That is why we're going to do this exercise. So great. So we know the current in the direction of current in the conducting wire. If we hold it like this such that the thumb points in the direction of current, then the direction in which my fingers are curling, look at this. If the direction is upward, current is upward, I'm holding like this, great. My thumb is also pointing upwards. What direction are my fingers curling in? That is the direction of current, which means if my fingers are curling like this, my fingers are going from right to left to hold that wire, then the direction of magnetic field is right to left. But what if it's in the downward direction? I'm holding it like this, right? Now, how are my fingers curling if I want to hold this wire? They are going from left to right, curling from left to right, right? That is how we get to know the direction of current. Now, if you imagine you're holding this wire that I have drawn, imagine you're holding it. How would you hold it? Would you hold it like this or would you hold it like this? You would hold it like this because the current is going upwards, right? So you hold it like this. So which direction are your fingers curling in? Right to left or left to right? Think about it. It is going from right to left. So the magnetic field direction would be from right to left. Look at this direction. This is like this, right? This is right, this is left, so it is going from, sorry, this is right, this is left, and our fingers are going from right to left, so it is in this direction. And it is not from left to right, it is not like this, because our finger is not curled in that direction. So now I can easily draw the direction of magnetic field. Okay, don't get confused, because here we have the direction, we are in this direction. Here in this part, it looks like the magnetic field is going from left to right, right? That's not what we mean by it. Let me show you what I mean by it. It would be clear if I draw the same wire with opposite current in it. If it is in the opposite direction, the same kind of field lines, we know the shape of the field lines formed are concentric circles, right? Now again apply the right hand thumb rule. Current is in this direction. What direction are my fingers curling in? They are curling from, you do it yourself also, okay? Don't just look at me. Unless you do it yourself, you won't understand. So my fingers are curling from left to right. So where do these arrows go? From left to right. This means from here to here. So it goes like this, right? So obviously the direction is in this direction. So it goes like this, here and here. Now, can you compare these two? Look at this. Is the direction in this part and the direction in this part same? No. So even if it looks in some place like it's going in the opposite direction than we thought it would, don't worry. Just trust your mind. Trust the rule that you have studied. You've studied the right hand rule and draw the arrow according to that only. Okay? Great. Moving on. Now, we have a question. Okay, so the question says that a current through a horizontal power line flows in the east to west direction. Okay. What is the direction of magnetic field at a point directly below it and at a point directly above it? Okay, great. Now, let's first draw what is given to us. Okay, if this is the power line, right? This is the AB. Let's say this is the power line AB. Now, what is the east to west direction? We know this is north, this is south, this is east, and this is west, right? So if we're told that the current is flowing in east to west direction, that means from right to left, from east to west. So how is the current flowing? The current is flowing like this. Now we're going to apply the right hand thumb rule. Now we have to find the current here, directly above it 1 and directly below it 2, right? So there are two ways to do it. Now if you are just standing here and doing it from this point of view, how you see the wire, it is going to be difficult for you, because then you'll have to say like either it is coming out of the plane or going into the plane of the paper. So how we do this question is, we imagine that we are either standing at the B end or we are standing at end A, which is B is the east end and A is the west end. So think about if you are standing at the end B and you are standing in a way that the wire is looking like this to you, like this is the wire for you. You are standing in that way. Okay. Now think about if you are standing at B. I am standing at B, and is the current going away from B or is the current coming towards B? The current is going away from it. Okay. So this is the wire. Okay. The wire to you in the question is given like this. It is given in a straight line, right? It is given like this. But I want to view it like this. So I have to go to either one of the ends, either A or B. The wire is given to you like this. I want to change my orientation, but I have to keep in mind the direction of current. Okay. So I go to the B end. This is my B end for me. Okay. So I am viewing from the B end. The current is going in a direction away from B. So what do? I hold the wire. I think like I'm holding the wire. I don't actually go and hold the wire, but I imagine that I'm holding the wire. Even if this wire is not there, I imagine it is I'm holding it like this. So I hold it in a way that my thumb is pointing in the direction of the current, right? Now I apply the right hand thumb rule. So I have to think about directly above it. That means here, somewhere here. So if I'm curving my fingers, up directly above it, I can see that it's going from left to right, or what do we call left to right? We call it clockwise, right? So if we say, if I'm viewing from the B end, viewing from end B or east, right? It is the east side of it. What happens at 1 or the point directly above it? The magnetic field is clockwise at a point directly above it. Now at a point directly below it, again I imagine this is my current flowing direction. Obviously my thumb is in this direction and I want to see below it. I can't do this because the current is not coming towards me. It is not coming towards B. It is going away from it. But if my fingers keep curling like this and they go below, what would their direction be? From right to left. And what does right to left mean? It means again clockwise, right? So again the same thing happens, that magnetic field, the magnetic field is clockwise. Same thing. Now, if I think about viewing, I'm doing both the things for you. You will only do one of them, but I'm doing it both for you so that you don't get confused. So I say that viewing from end A or west end, right? So now what is happening? My wire is given to me like this, but now I want to view it like this, and I am standing at the end A. So is the current coming towards me or is the current going away from me? The current is coming towards me. Look at the figure. The current is going towards A, right? So obviously my thumb will be pointing towards me. I curl my fingers. So what happens? At a point directly below, I can see that if I do it, it might be mirrored for you in the camera, right? So you have to do it yourself and the answers will match. So at a point directly below it, I can see it's going from left to right, which is anti-clockwise. So I'll do it for 1, but I did it for 2, which is the directly below it. Magnetic field is anti-clockwise. Okay, and if I do it same for the point above, if I take my fingers to go like this, I'll see that they're still going from right to left, which means magnetic field is anti-clockwise. That means it depends on where you're viewing it from, obviously, right? If you're viewing it from one point and then you go exactly to the opposite point of it, it would look like it's going in the opposite direction. Okay, great. Okay, let's move on to the next. Says draw the magnetic field lines around a bar magnet. Okay, will do. So we learned that this is the shape of the magnetic field lines around a bar magnet, north, south. So the thing we knew was they look like this, right? They look like closed loops like this, and we don't show it, we don't represent as such the loop lines going inside the bar magnet. Okay, let's show 2 here and 2 here also, and 1 that goes straight. Now the direction, tell me here, in which direction do they go? They go from north to south, so obviously in this direction. This one, which direction? North to south, so this direction. Now come down here, this one, which direction? Outside, north to south, so this direction. This one again, outside, north to south, so this direction. And these straight lines we know, north is the exit and south is the entry, right? Great. You can write here on the side that inside the bar magnet, the lines, magnetic field lines move from the south pole to the north pole. Okay, great. Let's move on. So it says list the properties of magnetic field lines. Okay, let's list the properties. Do you remember what the properties were? The first property was that they form, I'm writing it in short form, they form curves that are closed or closed curves. They are closed curves, right? This is the first property. The second property we learned was that inside the bar magnet, what is the direction of field? Inside it is from south to north, and outside you have to write complete sentences for this. Okay, I am writing it in short. Outside, they go from north to south. The third property we learned that the intensity, right? The intensity of the magnetic field is more when magnetic field lines are close together. Okay? But the fourth thing we learned was no two field lines intersect each other. Okay? These were the four properties that we learned. Now, the next question asks, why don't two magnetic field lines intersect each other? That's the fourth property we studied about. So, this is a very good question. So, for that, I'll tell you that if you take a compass needle, right, and you put a compass needle here, where would it, where it would point? It would point like this, somewhere in this direction. If you keep it here, it would point like this. If you keep it here, it would point like this. If you keep it here, it would point like this. If you keep it here, a little like this. And if you keep it here, it would point like this. What does this mean? This shape that I am drawing of the compass needle, this shape basically tells the direction of the compass needle. So, this shaded part would be the north and the other part would be the south. So, obviously, the shaded path, the north pole would not of the needle would not be near the north pole of the magnet, right? They would repel. So here, because it is the south pole, the north pole attracts. So the shaded part, which is the north pole, is near. So similarly, you can shade it for all the needles. So do you realize what this is showing you? This is actually showing you the direction of the field line. So at each point, the compass needle aligns itself to the direction of the field line. Okay, that much we've understood. Now, think about what would happen if the two field lines going like this, they intersect each other. What would happen if we keep a compass needle at this point? Where would the compass needle point? Would it point like this? In the direct, would it point, if this is one direction, would it point like this? But the direction of the other the other one is in this direction, right? Downward direction. One magnetic field line is like this, the other is like this. So in this case, the needle would point like this. So does it make sense? We said that the needle would point in the direction of the magnetic field line, right? But at the point of intersection, there would be two directions. Look at this. This is the intersection. One direction, two direction. In this intersection, which direction is the magnetic field line in? Can you say any one? Is it in just this direction? No, it is also in this direction because it is both intersecting. So what would happen? The compass would actually have to point in two directions at the same time to represent both these magnetic field lines, because that's what the compass does. But is that possible? Can a compass at one point in two directions? No, right? So that is why two field lines cannot intersect each other. Okay, so you can write it in this form that the compass needle aligns itself to direction of magnetic field line, right? But if two field lines intersect, then you can draw this figure like this. Then at point of intersection, what is happening? There are two directions, right? Obviously two directions that the fields are going in, two different field lines. So it would mean that compass needle would point in two directions, right? But we know that is impossible. But we know that's impossible. Therefore, we know that no two field lines can ever intersect each other because the compass needle can't point in two directions at the same time. Okay.